The drug thalidomide has a controversial history. Originally, it was prescribed to pregnant mothers to help them fight bouts of morning sickness, but was later discovered to cause birth defects in their children. Immediately after this discovery was made, the drug was removed from the market. However, as evidenced by the date on this prescription bottle, thalidomide has been making a comeback. Much of thalidomide's reactivity can be understood by taking a look at its chemical structure, and by the end of this lesson, you'll understand how chirality contributes to thalidomide's wide array of reactivity. Before we attempt to identify organic molecules as being chiral, let's take a look at a more traditional example, which is your hands. My right hand and my left hand are mirror images of one another, but if I try to put my hands on top of one another so that all the major features of each coincide, I could clearly see that although my hands are mirror images of one another, my right hand is not the same as my left hand. And that is the definition of chirality. A chiral molecule is non-superimposable with its mirror image, just like your hands. There are two methods we could use to identify a molecule as being chiral. The first is similar to the example we saw in comparing your right and left hand, and involves using mirror images. And the second method involves identifying symmetry planes and inversion centers within a molecule. First, let's take a look at how we could use mirror images to identify molecules as being chiral. All organic molecules will be either chiral or achiral. As we've learned, a chiral molecule is non-superimposable with its mirror image and must also contain at least one stereocenter. We could define a stereocenter as a tetrahedral carbon that is attached to 4 different substituents. And as this lesson proceeds, we will see several examples of stereocenters. It is worth noting that these are not two separate conditions. In fact, any molecule that is non-superimposable with its mirror image will automatically contain at least one stereocenter. However, when you are evaluating more complex organic structures, it is a good idea to try to locate at least one stereocenter within the molecule before you perform any rigorous test for chirality, because if the molecule does not contain at least one stereocenter, it cannot be chiral. Using the mirror image approach, the first step is to draw a mirror image of the molecule in question. If the mirror image is superimposable with the original structure, we will consider the structure to be achiral. However, if the mirror image is non-superimposable with the original structure, the molecule is chiral. Let's take a look at a few examples of this. Let's first take a look at chlorofluoromethane. If we look at the center carbon, we could see that it's connected to one fluorine atom, one chlorine atom, and 2 hydrogen atoms. Since it's connected to 2 hydrogen atoms, it is not connected to 4 different substituents, and this is not a stereocenter. Thus, before I perform any test, I know that this molecule is achiral. But let's see what happens if we perform the mirror image test. First, we could draw a mirror image of this molecule. We could see that this molecule on the right is a mirror image of the molecule on the left. And if we rotate this mirror image by 180 degrees about the axis that is indicated, we could see that the rotated molecule is exactly the same as the original molecule before reflection. Thus, this molecule is achiral because 1, it does not have any stereocenters, and 2, it is superimposable with its mirror image. If we move on to an example of bromochlorofluoromethane, we could see that its carbon atom is bonded to 4 different substituents, and thus it has a stereocenter. Having a stereocenter only tells us that this molecule might be chiral. We still have to perform one of our tests to prove that this molecule indeed is chiral. If we first draw a mirror reflection of this image, we can see that we generate this molecule on the right. And now if we perform the same rotation as we did before, we could see that the molecule on the right has the bromine group wedged and the hydrogen dashed, whereas the molecule on the left has the bromine group dashed and the hydrogen wedged. Thus, these 2 molecules are not superimposable, and thus this molecule is chiral. This method of using mirror images to determine if a molecule is chiral is very effective and will work every time. But if you are interested, I encourage you to take a look at Lesson 10, version 2.0, to learn about the second way in which we could tell if a molecule is chiral or not. With that said, whenever you are ready, proceed to the learning module for Lesson 10 and discover on your own the unique story of thalidomide.